Okay, so good morning, class. Can you hear from me? So in case I don't want to make sure there's no technical issue. No problem, right? Okay, thank you. Good. Okay, so maybe let's start today's lecture. Okay. So in the last lecture, last few lectures, right, we talked about the aerosol cloud physics and some aerosol or cloud chemistry, right? So before we continue, so do you have any question about the aerosol activation and also form cloud? Of course, we focus on a single aerosol, right? So in case you have an aerosol, if you know the size, the composition, okay, and also if we know the environmental condition, like the degree of supersaturation, right? So now you have some idea, okay? So whether this aerosol will activate it to form cloud droplet or not, right? So do you have any question about the aerosol and cloud activation? Okay, again, so if you have any question, so feel free to talk to me and also TA. So in case you have any question. So now, so we are going to talk about another topic. Let's talk about some mass transfer or mass transport, say to or from a aerosols. And of course, the one thing you can think about is we're going to talk about is like the condensation, right, or evaporation of a species, say from the aerosol. So that will have play an important role, right, to determine like the size or the mass or even the composition, right, of the aerosol. But one thing is why we are interested to talk about the mass transport is, so of course I understand like for those that you do the calculation or run the model simulation, right? So most of the time, so when you do this calculation or simulation, you assume somehow we can reach an equilibrium, right? Or we can reach a steady state, right? Within the time scale that you simulate or you calculate, right? But just for your reference or for your information, is that nowadays, so we know that for those who study the aerosol properties, so you will find that actually, so even for some evaporation or condensation process, chemical reactions, so in particular in the aerosol, okay, so we have called the mass transport limitation, okay. So that means that will have a huge implication in some of your model simulation, especially if you're interested to look at the aerosol physics or chemistry, okay. Of course, for the clouds is another issue, but the aerosol, so you need to think about the mass transport, okay, limitation. Okay, so this is just some background. So why we are interested to look at the mass transport, okay, or mass transfer limitation. So here we want to talk about the mass transfer. Or we say the mass transport, okay. Say to or from a aerosol or a particle, okay. So if you remember when we talk about the aerosol dynamics, right? So depends on the size of the particle. So we can define, so you can in the continuum regime, or you can in the kinetic regime, and also of course in between then we have the transition regime, right? So because of the behavior of the particle, right, will be very different in different regimes. So let's say if for this mass transport, so we talk about the transport, say in the continuum regime. So if you remember, the continuum regimes means that your particle size is much larger than the mean free path, right? The lambda here. And to define this, so if you remember, you can have this called the Nusselt number. So you can calculate the Nusselt number equal to the lambda. Lambda is the mean free path of your gas molecule, right? So this is basically the average distance, right? Travel, right, by the gas molecule before successive collision. So Rp is the radius of your particle or aerosol. So of course, sometimes people use the diameter, not use the radius, so just become dp. dp means the diameter. Rp means the radius of the particle, right? So if you are continuum regime, right? So if you remember, so that means that we have a large particle, say compared to the lambda, right? So that means although some number is small, right? Or say it's equal to 0. So then we are in this continuum regime. So now we are going to look at, say, the mass transport, say, to or from a particle, say, in the continuum regime. So let's say we define a particle. So R3 is the radius of the particle, and then we use the R coordinate. Okay. And then in the air, so you can have some species, say, so they can condense or evaporate from the particle, condense to the particle. Say you have some A, species A. So now when we talk about the mass transport, we can say that we're looking at, so what is the flux, okay, of the A, say, to or from the particle. Okay, so when we talk about the mass transport, so one thing is that we can, of course, talking about the flux, right? So therefore, most of the time you talk about the flux, so you will come across there's a JA and then comma, and then this R, okay? And then it's a function of R. R means so how far, right? So from the center of your particle, okay? So flux, because you know the flux can be changes, right? Across this radius, right? The R, okay? Depends on the R, right? So it depends on how far from the particle. So you can have different flux, or that means you can have different mass transport rate, okay? And also, so of course, if you don't reach the steady state, so this flux can maybe also change with time. So, but by the definition, this is a symbol JA comma R, right? And then you have this bracket R comma times the T. T means the time here. So this is we call the molar flux of A, right? So this is molar flux of A. So when you talk about the flux, and then we talk about the mole, right? So the number of mole of your A, right? So that would be mole, number of mole of your A pass through a cross-section area, let's say cm squared. Per time, right? So that means per second. So in this case, and then this is because it depends on the R. So that means how far from the particle this flux is at this different R position, right? And of course, you know the transport of the flux is due to the concentration gradient, right? In some cases. So therefore, you also have this C. Just to define some terms, is also C is the concentration of your A, right? So of course, you will vary in this R coordinate, and also can be depends on the time. So this is just the molar concentration in case because we're interested in the molar flux. So therefore, this is a molar concentration, right? So that would be the molar concentration of the A. So that means now you talk about the number of mole of A per cm cube of air, right? So at this R, okay. So this is just some definition of the term, okay. So now we want to solve is the mass transport, right? Say the flux, okay, of your A, say to or from the particle, right? So therefore, let's say we want to look at the diffusion of A, say to the surface of a stationary particle. So let's say we simplify our discussion, say we assume your particle is still in the air, right? So there's a stationary A here, and then you have a flux, right? Going to or from the particle. Okay. So therefore you can solve this mass equation, right? So if you want to look at, say, the concentration, okay, how the concentration of your A, say, in the air, right, change with time. And then if you know the flux, the diffusion, this is the molar flux of your A, say, to the surface of your stationary particle. So you can solve this equation. And then if you look at this flux, right, JAR means the flux of your A, right, at this R position, right? So you can just determine by the Fick laws, right? So this is tells you the flux. Molar flux is due to the concentration gradient, right? So along this R coordinate. So therefore, your molar flux, right, can also be calculated, right? So this, say you can say this is delta Z over delta partial, right? This is a partial, I think you know the symbol. So partial Z over partial R. So this is look at the concentration gradient, right? Across this certain distance. And then this is called the diffusivity of your species A, right? In the gas phase. So this is the BG, so diffusivity, right? Of the species A in the air. So then you can also substitute this back to this equation. So if we can just combine, say, 1 and 2, okay, so this is again, so this equation tells you, so if you know the flux, right, so how you would change the concentration, right? How a concentration of your species A in the air change with time, right? Due to flux, right? So if you substitute this one into here, say substitute combine say 1 and 2. So you can just combine these two equations, and then you can get this equations tells you how the concentration of your A change with time, of course, are related to the flux, right? So this is the equation. So again, this dG here is we call the molecular diffusivity of your A. Right, so you have the diffusivity of your A. Okay. You combine this. So therefore, we can kind of solve this equation, right? So if you really want to look at the concentration profile here. So we know that, so somehow to solve this equation, so you need to have some like we call the initial conditions or boundary conditions, right? So to solve this equation, so we need to give them some initial condition. Or we say you can need to provide some boundary condition. So let's see so what condition we can have, okay, and then can apply to this equation here. So if you look at, say, at time equal to 0, okay, at time equal to 0, so we can define some condition, say, so one condition is, so we can argue, so at time equal to 0, so therefore if you remember, so because the concentration, right, of your A will depends on two parameters. One is to say is how far, right, from the particle, center of the particle. And then of course, this is the time, okay. So therefore this is one is the R, one is the T, okay, here. So one thing is that you can see is this means that this is the concentration, right, of your A. Say when the R equal to RP means RP is the radius of your particle, right? So this is that means you are looking at the concentration, right? So you are looking at the concentration at the surface of your particle when we set that R equal to the RP, right? So this is the surface, right? So therefore you're looking at the concentration of your A, say at the radius or at the surface of your particle, right? At time equal to 0. So you can set this equal to the CS. CS means the surface concentration. And also you can argue so when your concentration, okay, say of your A, say very far away from the surface of your particle or from the particle. So at any time, okay, so the concentration is just a constant. So therefore, this is just a C infinity, right? So let's say you just far away from the surface of your particle or from your particle. So the concentration of your A is always constant, okay? And then you can always set that to say constant, have a certain value, right? So this is C infinity here. Okay. So given some of these initial or boundary condition, okay, then you can just apply to this mass transfer equation. And then if you also assume, say, a steady state, we want to look at the steady state concentration profile. So now that means you just further simplify the equation. So you can set, say, this partial C partial T, right? The partial derivative, you can set equal to 0, right? Because we just are interested to look at the concentration profile, right? Say along this radius, right? The R coordinate. Okay, but we're looking at the steady state, right? A steady concentration profile. So if you can apply this, so you can set this equal to 0. So now you can just see if you take this equal to 0, right? So set this equal to 0. And then these terms so also go away. And then you just left this term here, right? So basically, you can just set this equal to 0, and then you take this multiply, then to this side, so that will become 0, right? So because you divided by this one. So basically, your equation will just simplify to this one, and then with this the initial condition, okay? So therefore, you can solve this equation, and then it can give you the concentration profile, right? So you can solve this equation. So given this initial condition or boundary condition, and then you can solve this concentration profile, okay, at the steady state. So remember, we set this as a steady state. So that means that this concentration profile tells you, say, the concentration of your A, right? Say along this R coordinate, okay. So how the concentration change, right? If you do to this flux, okay. And then if we solve this equation, so you will come up with a equation. Say this is tells you the concentration, okay, of your A, say at a R position, right? So the R means so how far from the center of the particle will be equal to. So this is C infinity. This is the concentration of your A, say far away from the particle, and then this is a constant, say, and then can be minus equal to RP. Remember, RP is the radius of your particle. R is the coordinate, right? So the position you're looking at. And then you just have times this concentration difference, right? So this is the concentration, right, of your A far away from the particle minus the CS. Remember, CS is the concentration of your particle, or from your A at the surface, right? This is the CS. Or you can say this is surface concentration, right? So you can solving this. So this is give you the concentration profile. But most of the time, people will try to also rearrange this. So this, most of the time, you will see people present the concentration profile using this equation. C, this is a function of R, right? So because your concentration of your A will change along the R, right, coordinates. And then related to the concentration, say, far away from the particle, surface concentration. Yeah, and this is R is the radius of the particle. So any questions so far? So therefore, these equations give us some ideas about, so if there's a concentration, and then you allow some diffusion, right? And then so how the concentration, say, change along with this R coordinate. We can find this equation. Okay. And also now you have this concentration profile, but like one thing we are interested is to look at, say if you have a transport, right? Say to the particle. So let's say you just have the transport to the particle, right? So how this, so when you have this flux to the particle, so how the mass or the size of the particle change, right, with time, okay? So therefore, we also want to look at the molar flux. Say towards the particle, right? So therefore, if you want to look at the flux to the particle, so of course you are looking at the flux at the surface of the particle, right? So therefore, in this case, so you are looking at the flux at the surface. Okay, so now this equation tells you, say, how many moles of your A, say, will to or from the particle per unit time, I say per second. Now the JA, now I use the term J is different. So this JA means is the number of mole of your A, say, to the particle or from the particle, okay, per unit time. So this is per second. So of course, this will be equal to the flux, right? So of course, I need to know the flux. So now if you look at the flux, so you need to determine the flux, okay, at the surface of the particle, right? So therefore, so you have to talk about the flux, and then you just determine at the surface. That means that you will set R equal to RP, right? So because you're looking at the flux to the particle, right? So that means that you determine the flux at the surface, okay? And then because if you know this is the flux per unit area, right? Per unit time. So therefore you need to times the surface area, right? So this 4 pi RP squared is to give you the surface area of the particle, right? And then if you time the flux, right, across the surface area, right, of the particle, give you, so how many mole of your A, say to or from the particle, right? Does it make sense? So first you will determine the flux, okay, at the surface of the particle. So therefore you set R equal to RP. So this is the number of mole of your A, say across us per unit area per time, right? So now if you want to know how many mole of your A, say, to your particle, in this case, for example, per unit time. Then you need to times the surface area, right? Because you look at the unit. So this is the molar flux, right? And then this is the surface area. So now if you time these two, so this will give you the number of mole of your A, say to your particle. So then if you look at this, to be defined separate from this, I just get it tilted there. So if you want to determine, say, the flux, okay, of your A, say at the surface, right, of your particle. So of course I need to know the diffusivity, right, of your A at the surface of diffusivity of your species A. And then you look at the concentration, right? Gradient. Now you determine, say, at the surface, right? And then of course now you have this concentration profile here. So then if you can determine this, and then you know the concentration profile, and then you can have this, so you can determine the flux at the surface of the particle. And then if you solving this, so maybe let me just write down here. So that means now if you're solving this, so now you know the concentration profile, right? And also you can solving this, the flux at the surface of your particle. So then this is the molar flux to the particle here. So this is become 4 pi times the RP. RP, remember, this is the radius of the particle times the diffusivity of your species. And then you're looking at the concentration different, right? C infinity, right? Means is the concentration of your A, say, far away from the particle, and then minus the concentration, right, at the surface. So this is makes sense, right? This is the concentration gradient. So that means this equation will give you, say, the how many number of mole of your species A, right? So in this case, say, go to your particle, right? But now you can also look at this equation. So of course, we can argue, right? So this can be a transport, say, to or from the particle. So of course, you can see so whether the transport of the flux is from or to the particle will depends on this concentration difference, right? Okay, so that means that we can argue, right? So if your surface concentration, right, CS is different from the concentration, say, far away from the particle, of course, then you can determine, right? So in that case, then the particle can grow or shrink, right? So of course, if your concentration, say, of your species is far away, is higher than the surface concentration, right? So that means that, say, your C infinity is larger than your CS. So now you will have a condensation, right? So in case of your surface concentration is higher than the C infinity, right? So then you will have an evaporation of positive. So that this is just a statement here. And then of course, now you determine, say, this flux to the particle, right? So of course, when this particle grows and sink, so you can also try to look at how the size of the particle change, right? Due to the growth or shrink, or due to the condensation or evaporation of your A, right? So therefore, we can also see if you know the flux, right? So remember, this is the number of mole of your A, say 2 or from the particle, right? So then your particle will grow or sink. So now we want to look at, so also how's the size, okay, how's the size of your particle change, right? Due to the flux. Okay. So then you can also to look at right. So we also want to interest to look at so how the size change, right? So in case you have this flux, right, to or from the particle. So of course, this will be straightforward. So let me just remove this. So if you remember, so this JA here means the number of mole, right, of your species A, say to the particle. So that will be equal to just how the number of mole of the particle change, right? So with the size, and then if you know the density, and also if you know the molecular weight of this. So these terms is a 4 over 3 pi times RT to the power 3, right? So this will give you how the volume change, right, of the particle. And then if you time this, rho p means the density of your particle. Right? So now you know the mass, right? So how the mass of your particle change. But remember, so this JA is the number of mole, right, of your A. So therefore, you need to times the molar mass, right? MA here, this is the molecular weight of your A or molar mass of your A. So therefore, these on your left-hand side also give you, so the mole of your A, right, change per unit time or per second in this case. Because remember, so we need to have the volume times the density give you the mass change, and then times this the mole, or divided by this the molar mass give you the number of mole change with time, right? That means a mole per second. So that means the two sides are the same, right? It's the number of mole of A, right, per second. Okay. And then if you just rearrange this equation, and then you will find that because we are interested to look at, say, how the radius, okay, of your particle change with time. And then if you solving this equation, so we don't go into detail, but if we just solving this equation, so now this term, right, this is JA, so you have this term, right, so you just have this equation, right? So you can plug this into here, and then you do the rearrangement and then solve this. So how we can obtain this one is you can just substitute this one to here, and then you just rearrange the equation. You will find that. So this equation tells you so how the radius, right, of your particle change with time will be equal to dg, means the diffusivity, right, of your species A in the gas, and then times the molar mass of your A divided by the density of your particle. This is the radius of your particle, and then this is the concentration gradient. Okay. But of course, I think we somehow also highlight when we talk about the cloud droplet, right? So we can see here, right? So how the radius of your particle change with time will be just a proportional to 1 over your RP, right? You see, this is the radius of the particle, RP here. Just a note. So let me change the pen. look at these equations, so you will find that so this is how the rate of the particle, right? The radius of the particle change with time will be proportional to 1 over RP. So the implication, I think we also discussed when we talk about the aerosol cloud or the cloud growth, right? So that means a smaller particle, okay, will grow faster, right? So compared to the larger particle, okay, say compared to their size change, right, with time. And then also if you solve this equation, okay, and then if you just assume constant Cs and C infinity, so that means that let's say you assume these two terms are constant, and then they don't change with time, and then you just have this equation. Okay, hopefully you're okay with this, just to come across with that. But if you're solving this equation tells you so how the radius, right, of the particle change with time. Okay, so if you're solving this, so this equation, this RP squared is telling you, so at a given time t, so what will be the radius of your particle, right? Will be equal to, so this RP naught means your initial particle size. So before the condensation or evaporation, okay, so this is your initial particle size, and this is your initial particle radius, plus 2 times this dg against the diffusivity, right, of your A in the gas, and then this is the molar mass of your A, density of your particle. This is your concentration gradient difference, okay, between the concentration, say, far away from the particle, and this is the surface concentration, right, Cs, and then this is a given time t here. So therefore, this equation can tell you so how the radius of the particle change with time, right? Change with time, and then this is your initial particle size. Okay. Does it make sense? Any questions? So remember, so when we're solving this equation, so we assume you can use a steady state concentration profile. And then later we're going to show you that, so you also need to determine some time scale, okay? Because you can argue, right? So your concentration profile can also change with time, so due to the transform, okay? But of course, so eventually they will take some time and then they will come back and they give you back the steady state profile. So this process somehow has to be fast, okay, or in a short time, so that we can maintain steady state concentration profile. We're going to talk about this later, okay. So, but up to this point, so do you have any questions? So therefore, one major message here is, of course, now we will have some idea, say how, say the flux, right? And then how we change the size of the particle. And of course, one message, and also we have been highlighting these before, is if you look at these, so how the size of the particle change with time, right? So, and then you can see that this will be also somehow linked to 1 over LP, right? That means a smaller particle will grow faster than the larger particle. Any questions so far? Okay, any question? So now, so this is the flux, and then this equation tells you so how the size change with time. Okay. So of course, we also talk about, this is just the mass transport. And also you can see if you have a condensation or evaporation, right? Say if a condensation of the A to the surface or to the surface of the particle, or evaporation, right? of your species A from the particle. So this will also involve some energy, right? So we also need to concern about the energy. Okay. So therefore, I just want to quickly remind you. So we also need to consider some temperature effect or energy balance, right? So if you remember, because of course, I just highlight here again is because of this, say if now we consider the condensation or evaporation process, right? So you can also argue that some energy heat or latent heat is being released or absorbed, right? Because when we say this mass transport, say to or from the particle, so you are talking about some condensation or evaporation, right? So therefore, you can also argue, right? So you can have some heat, right? It's released or absorbed, right? So we also need to consider, we just, like I mentioned, we don't just do the mass balance, and we also need to do the energy balance, okay? So therefore, somehow, so people also, you want to also look at, say, yes, any question from the class? Okay, so therefore, you also want to look at, say, some temperature profile, right? So if you want to have a more accurate to determine, so therefore, you also want to have to understand some temperature profile, say around the particle. Right? Because eventually you also have to you need to also do the energy balance here. Okay. So of course, to simplify our discussion, so of course, usually most of the time, so we assume you can assume a steady state temperature profile around the particle. And then how we're going to do this is we can also estimate this temperature profile so we can also determine the temperature profile around the particle, okay, using this equation. And then this UR is we call the convective velocity, okay. Of the fluid motion. Say due to the concentration gradient. Okay. So you can have this we call the convective, okay, velocity. So as a result, because you know if we have some concentration gradient, right? So you can have some called the motion, right? The fluid motion, okay, due to the concentration gradient profile. So you have this term on your left hand side, and also of course you have this we call the thermal diffusivity. Okay, of your air. And then you look at so how the concentration profile around here. Okay, because we apply this kind of equation, okay, due to the concentration gradient for the gas phase species, and most of the time, in the atmosphere, okay, in the atmosphere, so the concentration gradient, okay, should not be that significant. Okay, so therefore, most of the time, we call this a convective terms, okay, or this convective terms can be neglected. So we can just neglect this convective term due to the concentration gradient. Okay. So therefore, you can also set this becomes insignificant. Okay. So that would be just equal, say, let's equal this equal to 0. Okay. So now if you're doing this, okay, apply to the atmospheric condition. So you find that your equation can be further simplified. It's very similar to our concentration profile. Because when you set this equal to 0, right? So you don't need to worry about this alpha, right? And also 1 over r squared. So then we will also go to the other side. Or if you take the constant. So therefore, if you're solving this equation, you will also can simplify this equation to just to more like the concentration profile terms, so that we have here. And then again, so we can follow the similar steps. So you can assign a initial conditions for your case. So for example, so you can assume, so your initial condition is you can say the temperature stay at the surface, right? So this is your RP, right? So let's say this is equal to your TS. TS is your surface temperature. And also you say your temperature, say away or far away from your particle is a T infinity, right? So you can have this kind of condition. And then you're solving these. So basically we get the same equation. You will also have so you also get this similar equation, right? This is at the steady state. This is the best at steady state the temperature profile, say around your particle. Okay, so this is the temperature, say at coordinate r, right? A certain distance, say from the particle r will be equal to T infinity is the temperature, right? Say just away from the particle. This is alpha is the radius of your particle r. Means a C. So we how far, right? Say from the center of the particle. So this is just the temperature difference, right? So Ts is the surface temperature of the particle. T infinity again is the temperature, say, away from the particle. So now one thing is if you to look at or to use this equation is we also need to look at or to determine this Ts. So I think we have to discuss this, right? When we talk about the cloud droplets. So when you have the water condensation, right? So if you remember, right? So if you have the condensation or evaporation, right? So you have this latent heat is released or absorbed, like we have the statement here, right? So therefore, your temperature of your particle can change. Okay. So therefore, I just quickly discuss here is that somehow we also need to determine, okay, this Ts, right, the surface temperature, okay, surface temperature here. So therefore, to do this, so we can also to do the energy balance. So now you're looking at your particle, okay. So first is you can look at the flux, right? So when you have a condensation or evaporation, right? So some latent heat is being released or absorbed. So therefore, the energy will be equal to so if you remember, right? So if I just have this flux, if I determine the flux R equal to RP means I determine the flux, right? Say at the surface of my particle, right? So that would be number of mole per area per time. And then if I times the surface area, right? So 4 pi rp squared. So this is the surface area of my particle, right? So then if I times these two, so I will just show you this is the number of mole of your A, right? Per unit time, say, go to the particle or evaporate from the particle. And then if I times this is the latent heat, right? So this is the latent heat or molar heat, right? So you can say, so basically this is the amount of the latent heat is say released or absorbed, right? So it depends on whether we have the condensation or evaporation. And then if you look at this energy, right? Or this latent heat, so there will be two phases, right? So one is we can say, so this heat, right? So one is of course they will being say kind of absorbed by the particle. You can transport inward, right, to the particle, or you can just release to the surrounding, right, to the air, right. So you can say, so you have this kind of heat conduction. Okay, so one is that you can say this heat can be just say outward to the gas, right? Or you can say you can have an inward into the particle, right? So basically, this is some of the heat will be say kind of retained by the particle, or some will just go back to the gas. So therefore, you can just argue so two terms, right? Or maybe I just write on the second row, so we have more space. Okay. So now basically you are going to have two terms here, right? So for this kind of a latent heat being released or absorbed, say by the condensation or evaporation process. So you have two terms here, like I mentioned here, right? So one is say you will just heat, say go back to the gas. Okay. So therefore this is the term here. So therefore this K, this is the thermal conductivity, right? Of the air, right? So because of some of your heat, right, would be say go to the gas phase, right? Go to the gas phase or go to the air, say by the combustion. So that is the thermal conductivity of the air. And then you look at the temperature gradient, right? Temperature gradient at the surface, right? Plus, so you can have some say heat, right? Say go inward to the particle. So therefore, this is called the Kp. So now this is the thermal conductivity, right? Of the particle. And then you are looking at the temperature gradient at the surface, right? So you're looking at the surface here. And then of course, this is to look at the surface, right? The surface area. So therefore, you times 4 pi rp squared. So therefore, you can solving this equation, and then you know the concentration profile and also the temperature profile here. So they can solving this equation, and then you can just determine the surface temperature Ts. Okay. So we don't go into details. Just show you the result. So what we are doing now here is you can solving this equation, okay, and then solve for the Ts, okay, the surface temperature, okay, of your particle. So this will be the result. Ts is the surface temperature of your particle, that is here, and then minus the T infinity, okay. So that means the temperature say far away from the particle will be equal to, this is the latent heat, right, of the say evaporation or condensation. dG is the diffusivity, okay, of your gas phase species, of the species in the gas. And then this is the thermal conductivity of the air. And then this is T infinity. So this is concentration difference here. Okay. So why we want to talk about this is again to remind you that if you really want to look at how, say, the mass flux change, okay, or mass transport, say, to or from a particle, of course, most of the time, so you may also want to, if you want to be more accurate, okay, to determine this mass transfer. So we also need to think about the energy balance. So this is one thing here. But the good thing is we found it turns out that so most of the time depends on the process, right? So how rapid of your process. I think we have some discussion last time. So in case your condensation or evaporation process is slow, okay, if your process is slow, okay, so then you can see that you don't have much amount of the heat is released, right? If you say your process is slow, that means your evaporation or condensation process is slow. So therefore you can argue, right? So you only have a small amount of the heat, right? Only small amount of the heat is released or absorbed, okay? So therefore, we can also argue, right? So we can also argue your temperature will not change that much, okay? So your delta T, so in this case, will also be small, okay? So therefore, you can also be assume you call the isothermal. So you can argue that your temperature of your particle is similar or equal to the temperature, say, in the surrounding. Okay. So you can make this as assumption, but assume this process is not significant. So therefore, you can also argue from this equation, right? So you can see here, right? So this is the concentration difference, right? So if you have a large concentration difference, means you can have a rapid or fast or significant, say, condensation or evaporation process. So that means that in that case, you can argue, right? So you may expect, so that certain amount of heat are being released or absorbed. So your surface temperature of your particle can be different from the surrounding here. But in case your process is slow, okay, so then it is safe to make this what we call the isothermal assumption here. Okay. And also one thing I think we mentioned last time is, especially for those if you are interested in look at the particle physics or chemistry, okay. So this is a very important parameter, the surface temperature of a particle, okay. Especially for some of these, if you really want to look at the fundamental mechanism of reaction or chemistry, okay, so you may not always can assume we call the isothermal process either, okay. So actually, indeed, some technique, they try to use this we call the thermal gradient, okay, say temperature of your particle and also the temperature of the surrounding. We try to apply this thermal gradient, okay, to do some reaction or levitation or things like that, because it can create a pressure gradient, if you have a temperature gradient. So therefore, it's very interesting for some of the studies to look at this surface temperature. Okay, but I can tell you that so this surface temperature is a very difficult to measure. Most of the time, so we need to do the calculation. Okay, so this is the case, but this is just for the information for those that if they're interested to look at the aerosol physics. Okay, so that means sometimes so people are interested to look at so the surface temperature or surface concentration or the CS. So these are two parameters that are very difficult to mention. So any questions so far? About like the mass transport, say to and from a particle. And also, again, so this is just to remind you that we also need to look at the energy balance, okay? So in case you want to have a more accurate, okay, determine the mass transport here. Any question? Okay, if not, then maybe let's take a 10 minutes break here, and then we'll come back at 12:41. Okay, so let's take a 10 minutes break. So in case you have any questions, so feel free to ask during the break. Okay. Kind of a quick review. So what we've been learned, some of these concepts, right? When we talk about the cloud, when we talk about the growth of the cloud drops, right? So, but of course, we change this in more like context in the Earth cases. Okay, or particle cases. So now we talk about the mass transport. Say, it's in the continuum regime, right? So that means that you have a large particle. Okay, and then in case then your size of your particle is much larger than your mean free path of your gas molecule. So therefore, your Looser number is small. Of course, we can argue, right? So the transport in the kinetic regime can be different, right? So if you remember, right, when we talk about the kinetic regimes, so that means that we are talking about some small particle. And then you can see if your particle size getting smaller and smaller. So in that case, we can argue, or maybe if you look at the Looser number, right, it become much larger than 1. And also because you're talking about some small particles, so when the size getting smaller and smaller, so they behave here more like a gas molecule, right? So if you with this kind of ideas. So therefore, now we want to look at see the transport, okay, to from a particle or to and from a say called a small particle. So in case we are talking about some kinetic regimes, so of course we are looking at some Looser number, say much larger than 1. So again, so if you remember, the Looser number is the lambda over LP, right? Or you can say 2 lambda over dp. So remember LP and dp. LP is the radius of the particle, dp is the diameter of your particle, right? So in case your particle is small, so now we talk about the small particle, right? So therefore, this number becomes big, right? So because of the lambda, the mean free path, of course, it depends on the temperature pressure, right? But the typical number is about 60, right, nanometer. Okay, so but this is more like more or less the same constant that the size of the particle can change, right? So that's why this is the case. And also, in that case, we just want to have some qualitative discussion here. Okay. So when you have a small particle, so you can imagine, right? So they behave more like a gas molecule. Okay. So therefore, for the molecules or for the small particle, so you can argue, right? So they have more like some random motion, right? So just like the gas molecule, they just have some random motion. They're just moving around here, okay? So therefore, you can we can also calculate, right? The number of the striking or collision frequency, okay? So in that case, we can also look at some of the number of collision or number of molecule. because you can see here is when we talk about the kinetic regime, right? So you have this small particle. They more or less they behave more like a gas molecule, right? They just randomly moving around, and then they can just strike the surface area. For example, if this is surface area, so if this is a small particle moving around, and then they can strike this unit area, right? So therefore, this number of the molecules striking us, say a unit area per unit of time, can be related to so somehow you can looking at this number of the collision events or the striking events is equal to 1/4 times this n. N is the number of your gas molecule or your total number of the particle. And then this C with the bar is the mean thermal velocity, right, of the molecule. Right, so this is a C bar means the mean thermal velocity, right, of the molecule here. And then if you remember, so you can calculate this, say the mean speed or mean thermal velocity, right? So that would be equal to h times the k. Okay, and then this is the times the temperature. This is the Boltzmann's constant, right? So then this is the pi. This m is the molar mass of your species, and then you take the square root. So I think we showed you this before. Okay, so this is a kind of your random number of the striking events that you will have. And then if you look at the flux, right, to a particle. So let's say this is your particle, okay. And then now, because you're talking about some small particle, so let's say this is your particle, you have some small particle, okay. So you can just argue, right? So the mass transport is more like it have this kind of a collision, right, to your particle, right? So you can have kind of this kind of a collision here. Okay. And then your mass transfer is a kind of a consider this kind of a collision events, right? That happen, right, to your particle. So therefore, if you say under this kinetic regime, if you look at this mass transport, say to and from a particle, so it kind of consider this kind of the striking events plus your particle surface area, because your particle surface area allow this kind of a collision can happen, right? So therefore, you can argue, right, kind of the flux. Now I put down a K here, means we are talking about in the kinetic regime can be proportionally. So I just qualitatively discuss, okay? So of course, there will be so kind of the surface area of a particle, right? And then say, and then you allow the number of the collision can happen, right? So it's proportional to the number of the collision, right? Okay, per unit area per time. And then we need to times a alpha here, okay? So let me see here. So first, so this 4 pi RP squared, like I mentioned, this is give you the surface area, right, of your particle. So this is 1/4 times this n times this thermal velocity, mean thermal velocity of your molecule, right? So this will give you kind of this kind of a collision, right? Say per unit area per unit time. Okay. So I think this is kind of we call the flux, or we say you can say this is the kinetic flux. But one thing is we want to have this alpha here. So alpha here means is we call there's a term called accommodation coefficient. accommodation coefficient. So what that means is you can argue, right? So every collision, right? So this you can give you some ideas about the number of maximum, right? Collision can happen, right, to the particle. Okay, if you time these two. But remember, not every collision, right? So when you have say your gas molecule, say hit the surface, right? So not every collision they will just stay there, right? So some collision, say you can have case the collision, okay, but they will just bounce back, right? So they will not stick on the surface, right? On the particle, okay. So therefore, you have this we call the accommodation coefficients, okay. So to consider this kind of we call the bouncing off effect, okay. We can say this is the bouncing off. So therefore, you have this alpha. So maybe let me. So I want to spend some time this alpha. We call this accommodation coefficient. So you can also consider this what I mentioned here. It's called you can bouncing off, right? Bouncing off here. So these accommodation coefficients take. So you can consider this accommodation coefficient, okay, alpha, is to consider this kind of the bouncing effect, okay, because not every collision, the molecule, okay, the gas molecule, right, will stick on the surface of the particle here. So therefore, you can see this accommodation coefficient can range from 0 to 1, okay, 0 to 1. 0 means, so basically every collision, so the particle will not stick on the surface, right? 0 means, so that means that every collision, so they just bounce back, so there will no sticking, they will not stay on the particle. So 1 means that every time you have this collision, okay, so they just stick on the surface here. Okay. So you can also argue this accommodation coefficient. I would say you can also think about this called the sticking coefficient, right? Sticking. So 0% means that they not stick on the surface, right? 1 here means 100%, right? So they stick on the surface. Okay. So therefore, these equations are just we just a qualitative to discuss. Okay. So if you want to look at the flux, okay, say to the particle or from the particle in the kinetic regime. Okay, so you can calculate this. So if you look at the equation, so if people derive the equation at the kinetic regime would be so we don't go into detail to how to derive this flux to the kinetic regime. But now if you just agree with me of this qualitative argument, then you will get some insight to so why in this say the flux, okay, in the kinetic regime, so you will say this is equal to the pi rp squared. So why now is rp squared, so surface area, right, of your particle, right? So because you see here, right, in the kinetic regime, right, so you're looking at this number of collision events is related to surface area of your particle. Now you can see come up with the term with your thermal velocity, right, of your species A. So assume now you have the A coming in, right, your particle LP. So now you use this thermal velocity, right, of your gas phase species, and then you have this accommodation coefficient. So it can range from 0 to 1, okay. And then of course for these you also need to have a concentration gradient difference, right? This is the C infinity. That means the concentration say far away from the particle, and then you look at the surface concentration, right? you still need to have a concentration gradient, right? And that is a sticking coefficient here. So you can also compare to this flux, right, in the continuous regime. So this is we just show you before. So when we derive this, so this is the flux, right? So when we talk about in the continuous regime, so will be equal to just 4 pi Rp, not Rp squared in this case. This Rp times this is the diffusivity of your A in the gas, and of course you talk about the concentration differences here. So these are the two differences here. Okay. I just want to have go through this qualitative discussion, so you have some ideas. So why you become Rp squared. So why you have this called the thermal velocity of your species, gas phase species, and also have this sticking coefficient, or we can say accommodation coefficient here. So at least you have some ideas. So why these terms come in? Okay. When we talk about the kinetic regime. Okay. The reason is you don't see this, for example, for this called the accommodation coefficient, or this called the bouncing effect, right? So in this continuous regime, you don't need to have this one. So basically, you assume every time, because you have a very large molecules or large aerosol. So when you have this gas comes in, so every time they just assume they just stay there. Okay. So unlike the small particle, so you can have this called the bouncing off effect. We need to consider. So of course, you can just if you just take this the two ratio, just nothing fancy here. If you just take the ratio of this two flux, okay, so try to relate it. Okay, the flux in the kinetic and the continuous regime, right? So we just derive, so you will just have this. So you can just try to relate these two in case just nothing. You just take the ratio for these two. So in case you try to relate the kinetic regime with the continuous regime. Okay. And also one more thing. So we want to discuss. So yes, there's a question. So is the C missing in between the DG? So which G? You mean this one? So you mean what's the C? C means the concentration gradient. So if you look at the continuous regime, so I think this is the equation. Am I correct? So you mean that some terms are missing in this equation? I think there's a question from the student is this a continuous regime equation? So let me have a check. So I think this equation should be right. Okay, this is not a C. This is more like a blanket. Okay. So that's I think this equation is correct for the continuous regime. Yeah. To answer your question. So yeah, I think maybe I confused you. You see this maybe I think maybe when I write this continuous equation, so you think that's a C there, right? So actually this is the blanket. We're looking at the concentration gradients here. To answer, I hope try to answer your question. Okay, good. Yeah, so sorry for that. So I think in some case, time to time, so some of my handwriting, if it's not clear to you, so just let me know. Okay, so in case I think maybe you get confused, so that they may be too C to you, right? So in some cases you're right. So don't worry. So in case my writing is not clear to you, so just let me know. So thank you for your question. Okay, good. So anything else? Okay, just one more thing we want to discuss because so you are going to because when you talk about the aerosol physics, okay, in atmosphere, so the condensation and evaporation process are very important process that govern the size, the mass, and also the composition of the aerosol. So therefore, this kind of equation, so you come to use quite a lot. Okay, so it's good for you to have some idea, especially like if it's first time to introduce this kind of accommodation coefficient. In case you don't like these terms, accommodation, okay, so you can say kind of we call the sticking coefficient, right? Sticking, because remember, so like a sticker here, right? So every time, so when you have a gas molecule, right, hits the surface of the particle. So of course, most of the time we assume you just stay there or stick on the surface, right? But remember, so when your particle getting smaller and smaller, so you need to consider this we call the bouncing off. So even if you have a large particle, your sticking coefficient may not always be 1. So this is always a debate, especially I think for those who do the cloud droplet. Okay, so even you have a cloud drop, right? So you have a dilute solutions, and then you have a water vapor, right? Come in, right? So you think that the sticking coefficient is close to 1. I think most of the cases, at least in some old days, so people think that the sticking coefficient is close to 1, right? Because this is a water vapor, this is a water droplet. So people think that it's close to 1. But this is not always the case, okay? So because this can have a huge implication for those who study the cloud physics, okay? So the sticking coefficient is not also 1. One reason is, of course, you need to consider some the mechanics of the momentums, but also the surface property of the cloud is not just the water. Okay, so just for your information, because nowadays, so people know that you have a lot of the, like I mentioned, right? In the cloud droplet, you can have some organics, also inorganics, or have some surfactant, right? That means some surface active species, so they will stay on the surface. Okay, so that means that you are not looking at a pure water droplet. Okay, even you're looking at some diluted solution, say for the cloud droplet. So therefore, this sticking coefficient, okay, for water molecule, okay, to a cloud droplet is still an open debate. Okay, so that can be some implication for the cloud formation, cloud physics. Okay, so one more thing that we want to talk about, of course, we talk about two regime, more like a two extreme case. One is a continuous regime, that means you have a very large molecules or large particles. So now we go to this we call the kinetic regime. So you have some small. So we are talking about some small particle, right? Of course, we can have this we call the transition regime, right? So we have this transition regime. So remember, so we can also have this kind of transition regime. So if you remember, transition regime means basically the lambda is similar to the size of your particle, right? dp, and then your Looson number is close to 1. So we have called this kind of a transition regime. So in that case, people will try to, you will see equation. Of course, they can have different form, but they try to link the your flux, okay, in the transition regime, say to the continuous regime, okay. So they try to look at the ratio here, and then of course they need to do the correction. So don't worry about the form. So you can see in the literature, they will have different form to do the correction. Say the flux in the continuous regime, in the transition regime. So but what the equation showed here is this is the flux, okay. Say in the transition regime, and then so you can relative or normalize to this we call the flux at the continuous regime. Will be equal to just have some correction. Now, of course, you know they are not the same, right? So you do the correction, and then you will link it to your Looson number. Okay, so based on your Looson number changes, and then you can do the correction. So you can have a different forms and different phases here. Okay, so but don't worry too much here. But the idea is people can more or less can experimentally determine the flux, say in the kinetic, and also kind of in the continuous. So this is more easier to do the measurement in this two regime. But in the transition regime is more complicated. So therefore, they just try to have kind of this kind of a correction. So therefore, remember, so when you go to the transition regime, so now you switch the equation. Okay, so this is just a one form. So you can find different forms, okay, from different studies. But the idea is that they just try to look at this for correction. Don't worry too much. Okay, any questions so far? Okay, any question from the class? So now you have some idea about the mass transport, right? Okay. So like I mentioned, for this mass transport, or we say it's kinetic. So one thing is we also worry about, or we need to consider, is what we call the mass transport limitation. So sometimes, so we want to introduce this concept called the mass transport limitation. And then we can give you some example is in case we are interested to look at some aqueous phase reaction of chemistry. So we take this as example. So one thing we can argue, or we can use as example. So let's say, so we have discussed this when you cloud drop. For example, you have a aerosol or a cloud droplet. Okay. So now, okay, let me try. So this is you can have a cloud drops or your aerosols. So now you have some SO2 in the gas. Okay. So what will happen is, so you can have the SO2, right? So can diffuse across the gas and then to the surface of your drop or aerosol. Say, let's say maybe this is your cloud drops. So you have the transport, right? So you have the mass transport, say of your SO2, say to the surface of the drop, your cloud drops. So remember, so to be more precise, so of course they will say you need to cross the interface, right? So you have this, this is your drops, and then this is the air, right? So you have to cross this interface, and then you diffuse into your droplet, right? So what will happen is, maybe let me just give you the name. So you have this, so you need to cross this interface, right? And then of course, once you have crossed this interface, so now you go to the inside, right, or within the cloud drops, and then you can say this is some of this solution. And also, if you remember now, when you dissolve in this, so I think you have this idea, right? So these SO2 can also have the dissociation. Give you the ions, and also you can have the reaction, right? Say the oxidation, right? And then give you the something. Like last time I show you, so your SO2, dissolved SO2 or your ions can oxidize by the H2O2, right? So you can have all these, okay. So you can have all these process, right? So if you really want to look at, say this is an example, we can say this is called the production. Say if this is a kind of the production of the sulfate, right? From some aqueous phase reaction. So now the thing is, so why we are interested in looking at this, the transport rate, and also we're interested to look at we call the limitation. So you can argue, right? So you can have this diffusion mass transport rate. So you can have a rate across this interface, and then you have a dissociation, and also you can have some reaction rates, right? And then if you really, eventually, if you want to look at, say, your sulfate production rate, the overall production rate, so you can argue, right? So they may be limited by some of these processes. If some of these processes is slow compared to the other process, okay? For example, if I argue, say, the diffusion, okay, of your SO2 to the surface is a very slow process. But say across the interface fast, and all these reactions is fast, right? Compared to this diffusion. So now you can argue, right? Your sulfate production will be limited by the diffusion, right, of your SO2 to the surface of to your droplet, right? Does it make sense? So in case you have so many processes, right? So if some of these processes is slow compared to other process, then you can argue, right? So your production or some of your reaction can be limited by some process here or some transport here, right? So therefore, nowadays, people are interested to look at this kind of, we call the mass transport limitation, okay? Because they will have some implication for some of these. And one implication, of course, is to remember, we always talk about this kind of equilibrium, right? But of course, to achieve this kind of equilibrium, so what we need to know is we also need to assume this process very fast, right? And then you don't have any limitation, mass transport limitation here. So therefore, we're going to give you some discussion here. Okay. Of course, one thing you can argue is whether you want to talk about some equilibrium, or you can say whether you can reach a steady state, or you can say argue. So you need to always to do the kinetic calculation, right? So if you cannot make a steady state, or you cannot reach an equilibrium state, right? So then you need to do your kinetic calculation, right? So most of the time, so this is the case here. And also, just before we go into details, there's some reason we want to talk about this, because nowadays more and more evidence when people talk about the aerosol physics or the chemistry. So these can be some implication, even for those who running the climate model or air quality models. So I'm pretty sure most of the time, so you assume in your given time step or your simulation time step, so you assume you can reach an equilibrium, right? Or you kind of reach some steady state for some of your process. But I just want to, for your information, nowadays it's not always the case. Okay, so you need to pay attention. So even you run some of your model simulation. So this for information. Okay. So now we want to use these as example. Okay. Say production of sulfate from some aqueous phase reaction as example to look at this, we call the mass transport, or we say the mass transport limitation. Okay. So of course, to look at this production of sulfates, and like I mentioned, okay, so you can kind of separate into different process, right? So you can look at different process. Of course, the first step, like I mentioned, is first you have your SO2 has to diffuse, right, to the surface of your particle. So therefore, the first step is you want to look at so how fast, right, the diffusion of your species, right? Say from the gas phase so first of all, you need to look at so how fast, right, your SO2, so in this case, or some of the species say diffuse just to the surface of your particle. So you want to know how fast, right? And then, of course, if you really want to look into these, they sit on the surface, but they also need to across a kind of the interface, right, before they diffuse into the bulk or diffuse into the droplet, right? So you need to across the interface, right? So therefore, the second step, so you can argue, right? So we want to look at is the transfer, right, of your species across the interface, right? So you need to diffuse across the interface. So once you diffuse across the interface, so now you go to the bulk. So what will happen for the SO2, one in this case is some of your species can say hydrolysis or ionization, right? Ionize, okay. Or you can say have this kind of a dissociation. So then you can have some process. I use the aqueous phase, so I assume we are talking about some cloud droplet or water droplet. So, but this is okay. You can also apply for the aerosol, right? So you can also have this kind of aerosol phase. Okay. And then, so of course I can have dissociation, but remember, so for the reaction happen, right? So what will happen is we need to, for example, your SO2 you can oxidize, right? Or some of the species can oxidize by say H2O2. So what will happen for the reaction can happen, right? In the aqueous phase is you need to diffuse around, right? So your species after dissociation, you need to move around, and then somehow you find another oxidant, right? So then you can have a reaction can happen, right? So therefore, you can also need to consider we call the diffusion. Okay. If you assume this is an aqueous phase, then you have this we call aqueous phase diffusion. Say of the species, say inside the drops. So remember, so if you are across the interface and then you dissociate, but if you don't have the diffusion, so what will happen to your species? If you don't have the diffusion or your diffusion rate is very slow. So now you can see, because you diffuse like this, and then if you say this is you don't have much diffusion, right? So then your species will just stick on the surface, right? Oh, sorry. Can you still see from me? So my battery is low. Can you give me 1 second? Sorry for the cut. So let me. How about give me a 5 minutes break? So I try to find the plugs. Okay. So let's take a 5 minutes break here. Okay. Sorry, I'm really apologize because the battery is running low. Somehow I need to change to the other side of the board. Do you have any questions so far? Can you see from now? So are you okay? Okay, thank you. So again, so in case there's any problem on the writing, okay, on the board, so just let me know. So this I change to the other cases, okay. So maybe I just try to use this size so that I find there's some contrast, okay. But first again, so apologize for changing these settings. So during the lecture. So okay, so let's continue, okay. So because before we talk about this is you have 4 steps, right? So one is so you have this transport, right? So say of your SO2, say transports to the surface of your droplets, and then you need to cross the interface. And then once you cross the interface, then you have some dissociation can happen, and also you need to move around, right, in your droplet, because you can see if you diffuse the species, right, and then you were just moving around with the droplet. So therefore, the 4th step is we call the diffusion, right? Say just within the droplet, not in the gas phase, but you need to have dissolve. For example, you have A here, right? And then once you dissolve and dissociate, then you just moving around here, right? So if you're going to do this, okay. And then of course, once you do this, of course, you can say you can have another species coming in, and then you have a feed, and then you're moving around, and then you can have the reaction, right? And then you can have the chemical reaction. So the last one is also need to consider some chemical reaction. So we also have this we kind of called a chemical reaction, right? So this is the case, okay. And then eventually, so if you consider all these steps, okay, and then if all these process are significant fast or is fast enough, so what will happen? So then in case now we can assume this we call the Henry's law constant, right? So then if you all this process we just discussed, and then if the reaction is fast, okay, and then you can achieve kind of an equilibrium, okay, or steady state, then you can describe this kind of process or reaction, say using some of we call the effective Henry's law constant, because if you remember, so the Henry's law constant just telling you the distribution, right, of your species into your droplet, and the effective Henry's law constant, okay, will give you the idea, include like the dissociation and also the reaction in case you consider. Okay, but somehow if you can achieve this equation, is like I mentioned, right? So all this process has to be fast, right? Okay. So therefore, to achieve this, okay. So what we need to do is you need to have all these process is has to be fast. So that means just in terms of word, so you need to establish, right, the gas phase concentration, okay, profile is very fast, right? So you need to establish. So first, because you see you have this dissolution reaction, so somehow eventually you may just affect, right? You can somehow deplete it or affect the concentration profile, right? Around the particle. So therefore, to solve this issue, right? So what we need to do is you also need to assume you can reach this concentration profile very quickly, right? So this is the important cases, okay. And also I see from the screen, I understand, so there's some tilt here. So I will try to fix it during the break, okay? But so let's keep it here for this moment. So I will try to fix it during the break. Okay, so now you need to have a steady, but the idea is no matter what happens in your system, so you need to establish a steady, okay, concentration profile, right? So this is important things. So that means to establish this, so that means your gas phase diffusion has to be fast so that you can just reach your steady state very quickly. We can also say rapid, okay. So to achieve this, and of course, when you talk about across this interface, right? So that means this we call the transport, right? Transport of the species, say across the interface, is also fast or rapid, okay. So because if you don't have this fast or rapid, so you can see you just stick there, and then what will happen if you don't have this transport across the interface fast? So now you just your species, right? will just stick on the surface, right? So they will not go into the bulk, right? So they will just stay or accumulate on the surface. So therefore, you need to have, say, when they approach the surface, they will dissolve and then quickly go to your bulk, right? And then finally, of course, you need to assume, so when you have this kind of a dissociation reactions and also the dissolution, so all this process has to be fast. So basically, we just repeat all our argument, and then the key statement is that all this process somehow has to be fast, okay? So that we can assume there's no transport, right? Limitation in this kind of a process, okay? And then you can just assume kind of a steady state, okay? So now what we try to do is to look at, so if you say the diffusion rate, okay, and then the transport rates across the interface, and then the diffusion within the droplet, and also the reaction. So how fast this reaction we are talking about, okay, and how much time we need to kind of achieve a steady state, right? So this to give you some idea. So how fast this kind of the process here, okay. Okay, so the first thing we want to look at is, so when we talk about this, so we want to look at, so what's the characteristic time scale, okay? To say if you have a gas phase diffusion, okay, from the gas to the surface, so what is the characteristic time scale, okay? So now we're looking at, say, the characteristic time scale for the gas phase diffusion to a particle. So one thing is when we look at this kind of a characteristic time scale, okay, and also if you look at the diffusion, so what we remember, right? So one thing we want to look at is we want to have a steady state concentration profile, right? So therefore, this characteristic time scale. So we are looking at, say, so what is the time, okay, required by the gas phase diffusion to establish, okay, a steady state concentration profile. So the idea is to, say, achieve a steady state concentration profile say around the particle, right? So this is what we want to know, right? Okay. So by doing this, I just show you the equation. Okay. So this is the characteristic time scale, okay, required, okay, to achieve a kind of steady state around the particle. So of course, this will link to this called the diffusivity, right, of your gas phase species in the gas. And also you need to look at the time scale, right, the kind of the length scales here. So the length scales that we use is called the R square. So you're looking at the kind of around the particle surface, right? So you can also derive this characteristic time scale using the concentration, using the equation we derived before. So maybe we don't go into detail, but if you're interested to look at, so how we come up with this characteristic time scale, so you can look at the concentration profile, right? If you remember, so we show you this equation before. Okay, so this is the concentration, right? So we show you before. And then to determine kind of this characteristic time scale, so we can do run a process called the dimension analysis, right? So one thing is we can first step is if I use to get this, I try to show you qualitatively. So how to get this characteristic time scale is you can do some non-dimensional analysis. Okay. So one thing is you set this kind of dimensionless, okay, parameter. For example, we can set this tau equal to a time divided by the characteristic time scale that we're interested. So therefore, this will have no unit, right? And then you can define a x. And then you're looking at the radius, okay, in the r coordinate. And then you normalize by this Lp. Lp is the radius of your particle. And also eventually, if you look at the concentration C, so you normalize by looking at the C, you normalize, say, by looking at the concentration difference between your species and the C infinity, and also the C surface minus the C infinity. So what will happen, you will find that all these, say the tau, the x, and also the beta here, they have no unit, right? You normalize it, so you cancel out the unit here. Okay. And then what will happen is if you substitute these back to this equation, okay. So by solving, you just substitute this into this equation, and then if you solve this, I'll just show you the result. Maybe I can write down here. So now if you just substitute these and then replace these, let's say the C, the T, and also the R's here with the tau X and also the theta here. So you will come up with this equation, okay, by just substitute into this equation. And then if you just analyze all these terms, so I think for some of the fluid mechanics studies, so you will find that they have the similar order, okay, the same order, okay. And that means that the idea is all these terms, you can argue, if you look at the order of this term, a kind of an order of 1. So therefore, you can set this equation equal to 1. So this term will be also in the order of 1. Right? So therefore, in this case, so you come up with this tau dg. So that means this is the characteristic time scale that we are interested, will be just equal to 4 Lp squared, and then times this we call the 4 times the dg, right, to correct the average here. So this is how we determine this called the characteristic time scale, okay, for the gas phase diffusion to kind of achieve or establish the steady state concentration profile. So in case you are interested, so you can go through these steps. But if you just apply this equation, say to look at the characteristic time scale, so this is the Lp squared, this is the radius, right, of your particle, and then to the power of 2, and then divided by 4, and then divided by this dg means the diffusivity of your gas. Okay, so if we apply the typical diffusivity of the gas, so this is assume the diffusivity, okay, of a gas species. A typical value is about 0.1, okay, cm squared per second, okay. And then if you look at, then you can calculate your characteristic time, okay, with different particle size. So I have the number here is 0.1, 10, and also 100. Okay, this is a micron in size. So you just substitute this number inside here. So if this is the micron, so you will find that the time scale, okay, so very short, it's very small, right? This is 10 to the power minus 10 second, okay? And even for large particles, it's 10 to the power minus 4, okay? So therefore, that means to achieve a steady state concentration profile, say around a particle, it's very fast, right? So even you have a large particle, so this time scale is only about less than a millisecond, right? Less than 1 millisecond, and you can just establish or achieve a steady state concentration profile around a particle. So therefore, most of the time, okay, so the diffusion flux in this case is fast. So you may not have this we call the issue here, okay, the concentration profile issue. So any questions so far? Okay, so then we solve this, and then we give you some idea is now when you talk about the diffusion here, right? So this is a very fast, and then you can achieve a steady state, right? Profile very quickly around the particle. So that would be no problem. So now the next step is now you reach the surface, right? So you need to cross the interface, okay? So we're going to see how about the interface, okay? So what will happen across the interface? I think because of the time, so let me take a 5-minute break here for this break. So just 5 minutes, okay? And then we'll come back at 1:48, okay? And also during the break, I also still try to make it better here, okay? Again, so I apologize for today. So because I need to somehow connect to some power cords around here, so I just need to shift to this corner here. I understand some tilted and distortion for the writing, but in case you have any problem about my writing here, okay, so just feel free to stop me anytime, okay? In case you cannot see my writing clear, okay, or even have something you want me to explain in more detail, just let me know, okay? Okay, so let's continue. So remember now we show you some ideas about, so when you have a gas phase diffusion, right? So you have a spatial state diffuse to the surface, right? So you notice that this at least this process, okay, time scale. So we are talking about it's just a 10 to minus 10 for small particle, and also even for large particle, it's 10 to power minus 4. It's a millisecond. Okay, so it's a kind of a fast process. So now we want to look at the time. So we're looking at some characteristic time, okay, to see if we can achieve an equilibrium, okay, at the interface. Okay. So we want to look at see the characteristic time, say to achieve the equilibrium at the interface, because we just mentioned, right, for the interface, okay. So we also will offer kind of a resistance for the mass transfer. So the idea is to look at these characteristic time. So we are looking at a time for kind of a saturation, okay, at the surface of the droplet. So we kind of look at a characteristic time for saturation of the droplet surface or aerosol surface. Okay, so what's the meaning or argument we are talking about here? So let's say initially, so you have an aerosol or a droplet. Okay, so this is your initial state. So you assume you just have at time equal to 0. So maybe to make a simplified discussion. So let's say if a pure water so you have a pure water drop, okay. So that means at the initial, so you don't have any species, say, right? So you don't have any species. So therefore, at time t equal to 0, okay, the concentration of your species will be equal to 0, right? So at time t equal to 0, so your concentration of your species will also be equal to 0. Okay. Let's say you can set this, the radius is Lp, okay. And then at the phi infinity, so and then say the species, okay, say far from the surface. So let's say we also call this a P0. So this is your initial concentration of your species, okay, in the gas phase, but it's far away from the aerosol. But at the time 0, right? So because we have a pure water droplet, okay, so that means that you don't have any species, right, in the droplet. So that would be set equal to 0. Okay. So now you allow some of your species A and then diffuse, right? And then hit the surface or across the interface. So then what will happen is that after a certain time, so then your A will kind of saturate, right, the surface of the droplet, right? So we saturate the droplet. Okay. So therefore, at time tend to infinity or given certain time. Okay, so that means that T infinity means that you have after a certain time. So now your concentration of your species, you can argue, right? You reach kind of an equilibrium, right? And then this equilibrium concentration will be equal to just using the Henry's law constant, right? So if you remember, the Henry's law constant is that if you know the gas phase concentration of your species, you times the Henry's law constant. So this will give you the concentration in the bulk phase, right, at equilibrium. So this is just the Henry's law. It's the Henry's law, right? So therefore, what we are looking at the time scale here is to try to look at, say, increase the droplet concentration, say from 0, right, to this with kind of an equilibrium concentration, right? Because you start with a pure water droplet, and then from time to time you allow your species, right, to come across the interface, and then eventually you reach the equilibrium, right? So we're looking at the time scale here. Okay. So therefore, if you look at the time scale, okay, so we are looking at the time scale say for increase, right? Increase of the droplet concentration, okay. From the 0 to this equilibrium. Okay, so we're looking at the time scale here. So any questions so far? Because you need to cross this interface so that your concentration will increase, right, with time, and then eventually reach the equilibrium. So we're looking at this process here. So now I can try to draw a picture for you. So assume this is the interface. So this is the interface. Okay. You can say that so this is the air, and then this is your drop. So, and then this is just your interface, right? Your droplet. Okay. And this is your interface. Okay. So then you can argue, right? So you can have some flux, say to the interface from the gas. So let's say we call Lg minus. So just follow the symbol. I think we use in the textbook. And also remember, so you will also can have a flux, right? Say from the droplet to the surface to the gas, right? So let's say we call this Lg plus here. So now when we talk about the flux, okay, so of course, when you talk about the air, the pressure we use will be the partial vapor pressure of your species, right? So therefore, that will be using the P naught. Okay. And then when you talk about, say, the flux from the droplet to the air, so then we will use the pressure, right, at the surface. Therefore, we call this a PS. And also we notice that this PS can change with time. The reason why this PS, that means your surface pressure will change with time in this case, right? Because initially you start with a 0, right? So you start with 0. So that means that you don't have any of your species. But when you have this cross interface and you dissolve this, so your concentration increase, right? And also therefore your surface pressure will also increase, right? So therefore your particle touch the surface, right? On the particle surface, at the particle surface will change with time. So therefore, this is the particle surface change with time. If we are interested to look at the flux, okay, it's from the particle surface to the air. So therefore, it's PS, and then it's a function of time. Are you okay with this? So this is just the symbol. So remember the surface pressure, the pressure at the surface, right? So we change with time. So before you reach the equilibrium, right? So now you reach the equilibrium, then it does not change. But before that, okay, so your concentration will also change, right? At the surface. So now we want to look at the flux, okay? So this Lg minus means the flux of your A, okay? Say from the gas to the surface to the interface. Lg plus you can say is the flux, okay, of your species, say from the droplet to the air. Okay, so there's 2 flux here. So, so let's say we look at this Lg minus, okay, Lg minus. So this is the flux, right? So in case that we consider some small droplet, okay, so we can use so let's say I just follow the discussions, assume this is some small particle, right? So when we talk about the flux, so we talk about some collision, right? Collision frequency, and then you just time this accommodation coefficient, right? So this is called you can also say this is the sticking coefficient, right? So this is the thermal velocity, right, of your species A, and then this is the number concentration of your species A in the gas phase, right? So this will give you the collision, right? Number of collision events per unit area per time, and then you times this accommodation coefficient. If you remember, so I just rewrite very quickly. So if you want to calculate your thermal velocity, and also this is Na. So remember the Na is the number concentration of your species in the gas. So you can also using the ideal gas law. So you can replace this with your gas phase concentration, right? Over RT, right? So if you remember PV equal to nRT, so your number concentration can be replaced by the partial vapor pressure. That means now we use the symbol called the P naught, and then divided by the RT. So this is basically come from the ideal gas law. So then I can just substitute these 2 terms into here. Okay, so if I substitute this, so you will find that So you can see the flux, okay, from the gas to the interface will be become the alpha times this P naught. So again, so the P naught, I don't use the PA, I just use the P naught. I just follow the notation. So this is the partial vapor pressure of the species A, and then divided by the square root right here. It's a 2 pi times the molar mass of your A, and then times this RT. R is the gas constant, T is the temperature, and then you take the square root. So this is the kind of the flux, right? From the gas to the interface. So now, if you remember, right? So this is the flux, and then you can also have a flux, say, from the droplet to the air. And then if you argue at one case, so in case if it's an equilibrium, so in case we can reach the equilibrium, so that means that now your Rg plus will be equal to your Rg minus, right? So this is how we define this equilibrium state. Okay. But one thing is if two phases are not equilibrium. So let's say we are not, say, not equilibrium, right? So this is the equilibrium state. So let's say if they are not in equilibrium, say not in equilibrium. So now we remember, right? So this we call the vapor pressure at the surface, right? We change with the time because the concentration of your species will change with time, right? So if you keep have continuous distribution, right? So the concentration become increase and increase, right? And therefore your surface vapor pressure will also increase, right? Or change with time. So therefore, in this case, if before you reach the equilibrium, you can use the P naught. Then your vapor pressure, right, will become the PST, right? Become a PST. So therefore, if it's not, so then you cannot use the P naught, and then the P naught can be replaced by and also because we know that this PS, the vapor pressure at the surface is a function of time. Okay, so therefore this is this case. So therefore, if you put this back here, so now you will find that this is your Rg minus, and then you can also write down your Rg plus. But now you cannot using the P naught. So you will use the vapor pressure at the surface, right? But you know this is the function of time. If you want to look at the flux, say from the surface, right, to the gas, then of course you will use the pressure, okay, at the surface here. And also doing this. But like I mentioned, right, this is the surface pressure, this is the PS. Of course, this will link to your concentration, right? And link to your concentration. And also this will be changed with time, right? So this is also changed with time. And then if you agree with this, so now you can somehow relate it to your surface vapor pressure to the concentration, right, of your species, okay, from the Henry's law. So therefore, if you know the surface pressure, right, and then you times the effective Henry's law constant, okay. So therefore, in that case, so you will also you can determine the concentration of your species at the surface, right? So because they're using the surface pressure, so then you will determine the concentration at the surface here. So now, if you just substitute this back to this equation, so then you will get this expression. So what I just tried to do is I just substitute these, right? Now the PS as a function of time will be equal to the concentration of your species, right, at the surface as a function of time divided by the effective Henry Saul constant. So what I did, I just substitute into this equation here. So now you can determine, right, the flux, say across the interface. So you can have the flux. Remember, when you talk about the net flux across the interface, you need to consider the difference between these two flux, right? So if you want to look at the net flux, okay, across this interface. So you can just look at the difference, right? This is the net flux, say called the RL. L means the interface will be equal to the RG minus, right? So this is the flux from the gas to the droplet minus the flux from the droplet to the air, right? So these two terms. Okay. So now then you can just minus these two terms, right? So you have these. This is the RG minus. So this is the flux from the gas to the aerosol, the droplet across the interface. So this is the flux from, say, from the droplet to. Then you can just minus these two terms. Then you will have this that we call the net flux, right, across the interface. So by doing this, so there's nothing. Just take the minus and then just group them together. So you can see you can take the alpha together with the 2 pi MART, take the square root. This is the common factor. You just look at the pressure difference, right, between the two cases. Remember, this term is just the PS, right, as a function of time. I just change it using the bulk concentration, right? So now, if you look at this equation, and then you look at this is called the net flux, right? L. So if you look at the net flux, so we can also determine the net flux using this equation, right? The net flux. So if you remember the net flux. So I hope that I'm not sure. So let me rewrite this. So your net flux, you can also argue so if you look at the net flux, so you can, if you say this is now the condensation, so you have a flux from the gas to the droplet. So the net flux RL, right? So you have a net flux RL here. So the flux, you can also argue, is just the concentration gradient, right, across this interface. And then you look at the flux, say, diffuse into your droplet. So therefore, you use the diffusivity into your aqueous droplet. Okay, so this instructs the flux, right? Say to the droplet. Okay, so therefore you use the diffusivity of your species in the aqueous droplet times the concentration gradient, right? So this is the concentration gradient at the surface, right? So that would be just your net flux, okay? And then this net flux will be equal to this one, right? So you can determine this time as a function of time here. And then if you just solving this equation, I think I leave the details in the textbook. But if you're solving this equation, say from 0 to C equilibrium, right? So this is the time scale we are looking at. So you will find that your tau So if you're solving this equation, okay, and then looking at, say, from A equal to 0, right? So initially you don't have any species A, right, in your droplet, and then to the equilibrium droplet. So this is kind of the time scale to reach the saturation, right, of the droplet, say, across this interface. Now you have this tau will be equal to the RT times this effective Henry's law constant of your species A, and then time this is square root, this is 2 pi times this molar mass of your A gas constant, and then the temperature, and then this is the accommodation coefficient, right? Because we also consider so whether the sticking coefficient, right? So in this case, okay. But now if you look at this equation, so one thing is interesting is or for further discussion is, so of course this will be related to your particle size. But one thing is that you can see here. So this is the Henry's law constant, right? So if you remember, or more precise, it's called the effective Henry's law constant. Henry's law constant. So what's the implication here? So at least you can see from this equation, right? So if your Henry's law constant increase, so that means your tau will also increase. So what's the meaning? So the idea is so when you effective Henry's law constant increase or Henry's law constant increase, so that means you are talking about a more soluble species or more soluble gas, right? Because your Henry's law constant increase means you can dissolve more species, right? So therefore, you are talking about some more soluble gas, okay? And then if you have a more soluble gas, okay, so it will take more times for us to reach the saturation. I think this makes sense, right? Because this is a more soluble, right? If your gas is a more soluble gas, right? So that means you can dissolve more, right, of your A into your droplet. So therefore, it's a reasonable to think about that if it's a more soluble gas, so you will take more times, right, to reach the saturation or to reach the equilibrium, right, concentration, because you can dissolve more species. If your species, say, is less soluble, if they're not soluble, so basically you just can reach the equilibrium very quickly, right? So therefore, it does not take much time to reach the equilibrium state. And also, you can put another argument, means if we have a soluble gas, okay, so that means more gas has to come across, right? Come across the interface so that you can reach an equilibrium. So therefore, it will take more times, okay? Does it make sense? Okay. So therefore, more soluble gas means the idea is the more soluble gas means you will take more time, okay, to reach the saturation, right? So across this interface, okay. Just for your information, for typical gas, For example, for ozone, SO2, I have the numbers for ammonia, and also the H2O2. Okay, so all these are some common gas. So if you look at this tau, okay, so all their tau would be less than 1 second. Okay, depends on the Henry's law and also the droplet size, and also the accommodation coefficient. So, but the typical number, okay, to reach the equilibrium state is just less than about 1 second. So that means the idea is, so for soluble gas or for most of the common gas, so we can reach this equilibrium at the interface very quickly. So based on the number I show you here, so just 1 second, you can reach the equilibrium or saturation, okay, for the common gas we find in the atmosphere. Okay, so this will be the message here. Does it make sense? Okay. I think because of the time, so I'm going to stop here for today. So once again, so there's a question. So yes, you are right. So if you case, so depends on the here, right? So if you have a positive, right? So positive means you have a net flux to the concentration. Okay. So there's net flux to the particle. Okay, you are right. To answer your question, or any other question? So so if there's no further question, so I think that will be the end for today's. Oh, sorry, I missed your second part. Oh, okay, so you have another question. So the concentration DADR is a negative. Okay. So you look at this concentration here. So if you have a flux, so what will happen? So because you know, if you have a higher concentration or if you have a flux here, right? So what will be the negative sign? So you will have to say, if you remember, right? So if you need to have say the flux to the surface, right? Say from the air droplet to the air. So then your concentration, so depends on the notation, right? So that would be negative. So I agree. Does it make sense? Then that means that you to the particle is then it's a positive. So it's a negative. You're right. Did I answer your question? Yeah, good. Okay, great. So any other question? Because when you have a negative, then negative times negative is positive, then you have the flux, right, to the droplet. Good. Okay, so if there's no further questions, so I think I will come to stop here for today. So then I will see you next week. Okay. Okay, thank you.